everybody, getting ready to do chapter 11 of SAT Math Level 2 preparation. And for the classwork of chapter 11, piecewise functions, definitions, absolute value function, and a postage stamp function. You got 4 points that go into your notebook, have that out, and you got 20 points on your classwork sheet, have that out in front of you. Student name, date, period, and then onliners and homeschoolers, put your due date here. And we'll go right into the first page here that will go onto your notebook. Piecewise functions are defined by different equations on different parts of their domain. These functions are useful in modeling behavior that exhibits more than one pattern. A, graph the function f of x equals, and then you have these two different parts of the function here. You have 3 minus x squared if x is less than 1, and then x cubed minus 4x if x is greater than or equal to 1. So how would you graph that? You can graph this on your graphing calculator. The second test command displays an equal sign and 5 inequality signs. These return the value 1 if an x pixel satisfies the equality or inequality, and 0 if it doesn't. For example, x less than 1 will take the value of 1 for pixel values of x that are less than 1, and the value 0 for pixel values of x that are greater than or equal to 1. Enter 3 minus x squared, x less than 1, plus x cubed minus 4x, x being greater than or equal to 1, into y1. So this would be your y1 entry. For values of x less than 1, x minus 1 equals 1, and x greater than or equal to 1 would equal 0. So for these values only, 3 minus x squared will be graphed. The reverse is true for values of x greater than 1, so only x cubed minus 4x will be graphed. This graph is shown on the standard grid in the figure below. So here is that piecewise function here after you enter these specific key-in demands for that. Absolute value functions are a special type of piecewise function. The absolute value function is defined as the absolute value equals x if x is greater than or equal to 0, negative x if x is less than 0. The general absolute value function has the form of f of x equals a times absolute value x minus h plus k, with a vertex at hk, and shaped like a V. This would be like a V if a is greater than 0, and like a upside down V if a is less than 0. The vertex separates the two branches of the graph. H delineates the domain of all real numbers into two parts. The values are the slopes of the sides A. The absolute value command is in the MathNum menu of your graphing calculator. You can readily solve absolute value equations or inequalities by finding points of intersection. So there's a hint there. B, example B, if absolute value x minus 3 equals 2, find x. So enter x minus 3, absolute value x minus 3 into y1 and 2 into y2 as seen in the figure right here. Here's your graph. Here is x equals, let's see, down here into y1 and 2 into y2. So here's y2. As seen in the figure, the points of intersection at x equals 5. So that'd be here, and x equals 1, which would be there. This is also easy to see algebraically. If absolute value x minus 3 equals 2, then x minus 3 equals 2, or x minus 3 equals negative 2. Solving these equations yields the same solutions, 5 or 1. This equation also has a coordinate geometry solution of absolute value a minus b is the distance between a and b, thus x minus 3 equals 2, has the interpretation that x is 2 units from 3, therefore x must be 5 or 1. And then example C, find all values of x for which absolute value 2x plus 3 is greater than or equal to 5. So here's your graphical solution for this expression up here. And then here's your intersections here. Remember, that would be our solutions. The graphical solution is shown. The desired values of x are on or right and left of the points of intersection. X is greater than or equal to 1. Greater than or equal to 1. Meaning this part up here. Or x is less than or equal to negative 4, which would be these values here. All these values. By writing the inequality as absolute value x minus the parentheses negative 3 over 2 is greater than or equal to 5 over 2, we can also interpret the solutions to the inequality as those points that are more than 2 1/2 units from negative 1 and 1/2. So that'd be another way of looking at your solutions. You're 2 1/2 units from negative 1 and 1/2, which is right here. 2 1/2, and then negative 1 and 1/2. Okay, example D, the graph of f of x is shown below here. Here's the graph. Sketch the graphs of y times the absolute value of f of x, and y equals the f of the absolute value of x. So the y of the absolute value of f of x and y equals f of the absolute value of x. So since absolute value of f of x is greater than or equal to 0 by the definition of absolute value, the graph cannot have any points below the x-axis. If f of x is less than 0, then the absolute value of f of x would equal the negative of f of x. Thus, all points below the x-axis are reflected about the x-axis, and all points above the x-axis remain unchanged. So that graph would become this graph here due to these limitations up here to this function. Since the absolute value of x is taken before the function value is found, and since absolute value x equals negative x when x is less than 0, any negative value of x will graph the same y values as the corresponding positive values of x. Thus, the graph to the left of the y-axis will be a reflection of the graph to the right of the y-axis. We just reflect over here through our y-axis here. And then example E here. If f of x equals the absolute value x plus 1 minus 1, what is the minimum value of f of x? So, okay. Since the absolute value x plus 1 is greater than or equal to 0, its smallest value is 0. Therefore, the smallest value of f of x is 0 minus 1 equals negative 1. The graph of f of x is indicated. So this will be the graph of f of x here. Minus 1 would be your smallest value here. Step functions are another special type of piecewise function. These functions are constant over different parts of their domains so that their graphs consist of horizontal segments. The greatest integer function, denoted by within this bracket here of x, is an example of a step function. If x is an integer, then the bracket x will equal x. If x is not an integer, then bracket x is the largest integer less than x. The greatest integer function is in the MathNum menu as INT on TI-83 and 84 calculators. So you would find it there. So we're going to have to try one. Sketch the graph of f of x equals a bracket x, which here is your step function here. So we always revert back here to our greatest integer function here. 5 examples of the greatest integer function integer notation are, so for 3.2, it should be about here. We would revert back to 3 for that, which would be about there. And then for 1.99, we revert back to 1 for that one. 1.9, we revert back to the greatest integer there. And then for bracket 5, which is out here somewhere, it would just be 5 because there is no decimal or anything like that. It's not a fraction, so it's just itself. And then negative 3.12, which is about here, it reverts back to negative 4. The next greatest integer for that one would be negative 4. And then for negative 0.123, it would be negative 1. We'll be reverting back to the next greatest integer, be negative 1. And example H, what is the range of f of x equals bracket x over x? So enter int x bracket x over x into y1 and choose auto for both independent and dependent in table set. Set table start to 0 and delta table to 0.1. Inspection of table shows only 0s and 1s as y1, so the range is the 2-point set of 0 and 1. So this would be an example here of finding the range of this function here using your calculator for that. And that is lesson number 11, SAT Math Level 2 Prep. Animated PowerPoint math video, AOL.com for questions or course materials. Thank you very much.